Okay, so as I said, they were only suitable for small examples. They were eventually abandoned, but since 1986, modern Newton methods were used with advanced linear algebra. Numerical codes were used so that you can actually converge these problems properly without numerical difficulties. To achieve polynomial time complexity, each time mu is decreased, you perform only one Newton step, and with a suitable way, you reduce your mu value in the next iteration. So let's look at a small linear programming problem. We have this objective function in two variables, x and y. So this is my x, this is my y. And I have two inequality constraints, the yellow line and the green line, and I have my bounds x greater than 0. X greater than 0 is the blue line, and y greater than 0 is the red line above the 0 point, the origin. So my feasible region is in here, and including, of course, the boundary of the set. And if I used simplex to solve it and started from vertex 0, 0, I would move to this vertex and then to this vertex, which is the optimal solution. And I'm showing also the contour planes of the objective function as these parallel thin blue lines, the minimum being in that direction. So it's here. So how would we transform this to barrier problem? You take all the inequalities, including the bounds, and you append them to the objective as was explained before. In the following slides, I start with a mu from 100, reduce it by a factor of 2. For 10 iterations of this, I show the points which are the minimizers to each subproblem, barrier subproblem, which is called the central path, and it's not the path produced by interior point method solvers because they jump in the value of mu before converging fully each subproblem for fixed mu. So this is the contour plot of the problem with mu equals to 100, and you can see that the minimum is heavily biased to be at the center of this problem because the mu value is large. So there is the first minimizer. Then you reduce your mu from 100 to 50, you find the next minimizer. Reduce it to 25, you find the next minimizer to 12.5, and the minimizer continues to travel within the feasible region, and guess where it's going to go eventually? It's going to go there, but it's not going to touch it because the logarithms would become infinite. Okay, so you're always interior. And there is another one. So that's the end of the iterations. The interior point algorithm would actually do something like this. Again, staying interior, but it would take larger jumps. So the previous method is called the Primal Method because it doesn't use Lagrange multipliers, it just absorbs all the constraints into the objective, but it has shortcomings, primarily that it needs a feasible starting point to commence the iterations. Non-linear inequality constraints cannot be guaranteed to remain feasible within iterations, so that could be a major issue. And almost exclusively nowadays, what we find in practice is Primal-Dual barrier methods, where all nonlinear programming problems and linear programming problems can be cast into canonical form, involving equality constraints, which may be violated, and bounds, which are always satisfied and easily initialized. So you start from this type of problem now, where you have equality constraints and non-negativity bounds, And the only difference of what you're doing is you're absorbing only the bounds into the logarithm, while you're still subject to any type of equality constraint you may have. So this you can solve. And interior point methods constitute a success story. They can solve problems of the order of millions of variables. Even nonlinear programming problems have been reported to be solved to such sizes from within chemical engineering applications. They always converge within 30 Newton iterations, and regardless of problem size, more or less. And there are clear gains for very large scale applications. Applications of nonlinear programming. All previously examined formulations may result to an NLP, and therefore we need such capability to solve them. NLP solvers nowadays can reach, with interior point methods, as I said, up to millions of variables. For convex problems and linear programming problems, there are even reports of having gone up to 1 billion variables. But also now you can have not only offline applications of optimization, but also online optimization is possible. And this is yet another area where I'm introducing applications, which is called model predictive control. One of my students, Walter, is working on this area. And what we do is design fast, reliable, online, real-time optimizing controllers. So your controller is not only interested in maintaining stability or steady states and track desired set points, but it also can have a criterion within its objective which measures the cost of maintaining the process where it should be. So that's why I said you have an optimizing controller. It can be applied also in supply chain management problems and in revenue management. Like I think an application is the allocation of prices to airplane tickets according to how the plane fills up. So, what is the formulation? The formulation has an output, which is the control actions at each time instant. The input is the current state of your dynamical system, and it can handle disturbances. And the objective, as I said, is a mixture of control and economic criteria. And this is a diagram of how it works. You have your usual process block with inputs and outputs. The outputs are measured, and they go into a model predictive control optimizer block with a process model within it. The block gives you control actions which go back into the process, so you close the loop effectively with an optimization algorithm rather than just a PID controller. And also, from time to time, you need to refit your model because parameters drift. So you have a model identification block which adjusts the model for the controller every so often, or when there's sufficient drift detected, so it just engages in that. So that's how you can have optimization driving a process. This is the formulation. I'll just skip it because this is not what I want to show. Basically, this is how it works. You run an optimization problem, an optimal control problem, actually, let's say for 5 steps ahead into the future, while you're still standing at step 0. The moment you have an optimal solution, you take the control action for the first step and you implement it in the actual process, and while this is running, you remeasure your process and you run another optimization up to step 6, and then you take the first step that's available, you apply it to your process, and you move on like this. So with a longer horizon, you're trying to capture also the stability of the process or to ensure it. So this is how model predictive control works. Now, the other type of important algorithms that arise in many areas of industrial interest actually are integer programming problems, where some of your variables or all of them are integer or binary. Either it's because you're counting whole numbers. How many aeroplanes do I produce this year? How many aeroplanes do I need to buy if I'm an airline? You can't buy half a plane. Or because you're trying to capture embedded logic within your model. For example, if I want to include a heat exchanger here, or do I not include a heat exchanger at this point? It's a 0-1 variable which you somehow have to model with your formulation. They were addressed very early on, as soon as linear programming solvers matured, and they led to mixed integer linear programming models and solvers. I will focus in this presentation here on only binary variables, where integer variables can be handled in a similar fashion. And the problem complexity, if you have n binary variables, it means if you were to do it by complete enumeration, you would need to evaluate 2 to the n possible solutions, which is very large. It's an exponential explosion. If we were dealing with combinatorial problems, explicit enumeration is only possible for tiny, small problems. And how it's solved is typically by a branch and bound type of algorithms or branch and cut. And they're effectively implicit enumeration methods. They enumerate something, but they can discard parts of your solution space based on some properties, which we will see in the next example. But to give you an idea of exponential complexity, depending on the number of binary variables you have, n, the number of people is around here 7 or so billion. Then you have the number of galaxies, just a little bit above on a logarithmic scale. Then stars, Avogadro, a number of particles in the universe, and you still have not even reached 250 variables. So that's the number of solutions you would have to enumerate if you were naive enough to try such an algorithm. So how does it work? Well, what's so special, rather, about integer solutions? Let's say that we have an optimization problem, and these are the constraints. The lines here shown are constraints, and I'm only allowed to take integer values of my solution. So I have 1, 2, I have 0, 1, 2 for my variable x1, and I have 0, 1, 2 for my variable y. So if I were to treat this optimization problem, which is linear in some sense, it is linear. If I disregard the integrality of my variables, linear programming would give you a solution which is on the vertex there. So you might say naively, well, I can round it up or round it down. If you round up your solution, you're outside the constraints. If you round down, you have to go to the next integer here. You are severely suboptimal because your objective function is whatever this tangent line is giving me versus this line up there. So if you're lucky, you're feasible but suboptimal, or you are simply infeasible if you just round up and you don't satisfy the constraints. So there's no easy way by rounding up integer programming problems to get a good enough solution, unless they belong to a kind of special class you can approximate nearby solutions. But this is not the general case. So for what will follow in this section, keep in mind two things. If you add a constraint to an optimization problem, you add a constraint, it will either do nothing to the solution, so it's a loose constraint, it doesn't affect it, or it will actively constrain the problem so that the new optimum is smaller for minimization than is larger for minimization than what it used to be. So actually it cuts part of the feasible space, or it doesn't do anything. If I fix a variable to a given value, so let's say I have a variable which is 0.3, and I either fix it to 0 or I fix it to 1, then we'll either do nothing or it will result in a worst optimum, because I've just added a constraint to the problem. I said y is equal to 1 or y equals to 0, whereas in the previous solution it was 0.3. So it's like adding a constraint. So with this in mind, let's look at an example. This is an integer programming example where the variables, there's 4 variables, y1, y2, y3, y4. There's a reference from where this was obtained. And I have one constraint, and also this is a constraint, namely the fact that my problem is integer. It's 0 or 1. Now this is not convex. Why? The feasible space, this is a linear objective. But these two together are non-convex. Why?
Because they are not convex set.
Yes, why are they not a convex set? Which is the set of feasible values here?
Isn't it because like the y's can only take 0 or 1, so it's
correct.
Must be greater than 0.
Yes, the feasible space is not in here. The feasible space is the feasible points. So it's this, 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 not this, and not this, because that's not integer. So it's only like 6 feasible points that you have, and there's no convexity, because a straight line connecting these 2 points does not contain any point which belongs to the set. If you remember what convexity of a feasible set was. Any 2 points in the set must, when connected by a straight line, all the points on the line must belong to the set. And here you don't have such a thing. So that's non-convex. However, it's linear, and we can exploit that. So we begin by solving the relaxed problem. We ignore the fact that we had 0, 1 constraints, and we say, just relax y within the range 0, 1. I can solve this readily with the simplex method, or any method. So when you solve it, you find that the optimal objective is minus 22, and also that all of the variables are integer, 0, 1, except the third one, it's 0.5. So it's not good for us. However, we have a valid lower bound for what we expect the optimal solution to be. Okay, and that should be clear why it's a lower bound, because you have a convex set which contains your set entirely, and you've moved to the lowest point of the objective from the container set. So you've relaxed it, and you found a lower bound. Okay. And then we do what I said we will do, which is the fractional variable. I'm going for it, and I'm going to fix it either to 0 or to 1, and then resolve the resulting linear programming problem with all the other variables loose. Okay, so this one gives a fractional solution of minus 21.85, so it's worse than the lower bound. And this gives you minus 21.65, again, a fractional solution. And I may choose either one of them to branch again on the fractional variable. So I chose the upper problem. And this gives you a fractional solution, again 21.8. And this gives me, magically, an integer solution. So from this, I will not need to branch further. That's minus 18. And it is also a valid upper bound, because it's the first integer solution that was obtained before exhausting all the tree. So I know that my solution is validly between minus 22 and minus 18, with minus 18 being a possible fully integer solution. But is it the best? We still have this side here, and if you branch on that and the other one, you find another integer solution here, which gives you, this was the integer solution we had, and you get another integer solution if you branch from that, which gives you first an infeasible branch, here an integer solution of minus 21, which is worse than this. No, actually this is better than this, sorry, you're minimizing. Beyond this we don't have anything, and beyond this you don't have anything. This one I think gave an infeasible further problem, and so you obtain the global solution, which is minus 21, with having solved 1, 2, 3, 4, 5, 6, 7 problems, rather than having solved all the 2 to the 4, which was 16 problems. That's why it's called implicit enumeration, because if I find an infeasible problem there, there's no need to further expand. If I find a lower bound which is already higher than an upper bound, no need to expand it, because it's a lower bound and it's already worse than an upper bound. So implicitly, you are fathoming part of the tree without having seen it. And all because your problem is convex, and in this case, it's linear. So branch and bound can prove global optimality of a solution. It can be terminated in fewer iterations than complete proof of global optimality. I may prescribe a tolerance between my two bounds and terminate earlier, because it might take still combinatorial time to converge. It provides rigorous bounds for the solution, which is a good thing, and usually terminates before it becomes exhaustive. It can be used for both mixed integer nonlinear programming as well as for mixed integer linear programming, but guarantees of solution for mixed integer nonlinear programming you can only have if your problem has a convex formulation, the relaxed problem, if it's convex. So where is integer programming applied? It's applied in a number of applications, in process synthesis, in scheduling, and in transportation problems. So let's have a look quickly. In process synthesis, the key idea is as follows. Include a sufficient number of alternative processes, units, and interconnections. Have binary and continuous variables decide which is in and which is out. Decide the connectivity. Do I have a connection here or do I not have a connection here? The operating conditions, and the overall model is called basically a superstructure, because you contain, if you know that you need 2 distillation columns, but you include all the other possible options, then you create a superstructure to select out of all of them the 2. So this is an example here. If I have to synthesize multi-component distillation and I consider simple binary columns as my process unit, then I can either cut ABC, a 3-component mixture, into AB and C at the bottoms, or A at the tops and BC at the bottom, and then cut it further at B and C. So I only have 2 possible sequences. You might say, that's not a big issue. Well, how about when you have 5 components? Where in this case you have 15 sequences to consider how to separate out the components. You can have integer programming make the decisions for you to find the best, most economical distillation sequence to design. So for many components, this is the number of separations and sequences that you have, which, as you can see, it really grows quite large. Of course, you wouldn't design 30 component separations. This is just to show the complexity. Another application is in heat integration, where there is an analogy of heat recovery network with a transshipment model, where you shift energy from one source to another sink, and those are the temperature intervals from a pinch analysis. And this is some old work that was shown in 1980s, 1983. And finally, one area where we made the initial papers, we published the initial papers before 2000 in this department in collaboration with Professor Wilson, is formulated as an MINLP, where all possible stream splits, not the heat exchanger network. This is the next application, is our application. This is the design problem that was considered by some people in the States, where they tried to design heat exchanger networks considering all stream splits, all stream mixes, and all possible bypasses. So basically what they gave to the optimizer is this thing here, which allows for things to bypass, to connect, and to form any network feasible for the data you have, for the streams you have. But it's a non-convex problem, and it's very hard to solve. Now, so the scheduling thing is where I will demonstrate some of our work. And basically, the key ideas in scheduling is where you have multi-period operations, you have binary variables on-off with indexing, so time, at which time, which unit will be used, and what process will it carry out. You have continuous or integer variables for quantities, for flows or inventories. And the applications are in batch scheduling or production planning, supply chain management, and scheduling of maintenance operations, which is work which is still ongoing in the department with Sai sitting at the back. But it was started many years back with myself and Professor Wilson. And basically, I'm showing you an example. We have this, I think, 25 heat exchanger network, which is the preheat train of cold crude oil. You want to preheat it with various hot streams that are available, the pump arounds from the distillation columns. And eventually, you want to maximize the energy recovery with this integration so that you have the maximum entry temperature into the furnace, because then the furnace has to give you a fixed set temperature for the first distillation column. So the lower this temperature is, the more energy you have to spend. So you have to have good performance of the heat recovery network to work. Unfortunately, fouling, which makes the surfaces of the heat exchanger dirty, reduces the heat transfer capability, and therefore you have to periodically decide what to clean and when to clean it. And this is the result of some integer programming work we did early on in the 2000s for scheduling the 25 heat exchanger network over a period of 3 years. So, yes.